All right, looks like we're good. Let's go ahead and dive in then. We'll start out with properties. Same properties that we talked about on Monday, commutative with a T, associative, and identity. And just as a little reminder, commutative is about order, associative is about grouping, and then identity would be, is there something we could subtract from a number and have that number retain its value? And does that work both ways? So that's what we'll look at for identity. There's not really a one word summary I can give for identity. But let's go ahead and start by looking at commutative. And we'll start out with just, I'll ask you a question. 7 minus 5, is that equal to 5 minus 7? Yes or no? And I won't make a poll, it's just a question. Is 7 minus 5 the same as 5 minus 7? Are those equal to each other? Got a couple yeses and a couple nos. We're split on this one. All right, well, 7 minus 5 would be 2. 5 minus 7 would be negative 2. So I'm going to stick with the fact that those two are not the same as each other. And now we've got that more consistently over there. So 7 minus 5 and 5 minus 7 are not the same as each other. If we're going to say that the commutative property is true, it has to be true all the time, no exceptions. Well, clearly, the commutative property doesn't work with subtraction because right here is my counterexample. My counterexample that proves the commutative does not work for subtraction, because there you go. It'd have to work all the time if it worked. Here's the case where it doesn't. So commutative does not work. There is no commutative property for subtraction. We have commutative for addition. We do not have it for subtraction. Similarly, let's look at the associative property. If I wanted to say 5 minus 4 minus 3, would that be equal to 5 minus 4 minus 3? I'll give you a second to decide whether or not that's true. And notice, we haven't changed the order. All we've changed is the grouping. And if we change the grouping and those two are equal to each other, then sure, associative could work. But if we change the grouping and those two are not equal to each other, then associative doesn't work for subtraction. We've got some no's over there. That's good. Let's see what we get here. We would have to do order of operations, do what's in the parentheses first. So this would be 1 minus 3. That would be negative 2. On this other side, we'd have 5 minus, 4 minus 3 would be 1, which is 4. Not the same. Associative does not work for subtraction. And so, nope, we do not have an associative property for subtraction. Commutative worked with addition, does not work with subtraction. Associative worked with addition, does not work with subtraction. So there is no associative property for subtraction. Negative 5 minus 7, 7 minus 5. Well, Joanne, let's take a look at that one. The numbers aren't the same, right? Because we got negative 5 minus 7 and 7 minus 5. So this one, they're both subtraction. This is a positive 5. This is a negative 5. So the numbers aren't the same. But even looking at those numbers, negative 5 minus 7 would be negative 12, and 7 minus 5 would be 2. So it doesn't work that way either. Okay, let me see what we've got there. So if we did negative 5 minus 7, and then negative 7 minus 5, in this case, negative 5 minus 7 would be negative 12. Negative 7 minus 5 would also be negative 12. And this raises a really good point, Joanne. It's possible for us to find a place where it does work, but if we're going to say that there is a commutative property of subtraction, it has to work every single time, no exceptions. We might be able to find one where it works, but finding one time where it works is not the same as saying this is a property that works all the time, every single time. Instead of finding one example where it does work, which may or may not be true. We can also find one example where it doesn't work, and that's enough to say, nope, there is no commutative property for subtraction because it doesn't work all the time. It doesn't work every single time. That's a good point to raise, though, Joanne. I appreciate that. But all we need is one counterexample, and we say false. We say there is no commutative for subtraction. Similarly, you say there is no associative for subtraction. And then identity, I think you probably know where this one's headed. If we say 9 minus 0 equals 9, well, sure enough, then we started with a number, we subtracted something from it, and kept the same value of that number. That looks like the identity property. But in order to have an identity property, this has to work both ways. And so then I go 0 minus 9, and I get negative 9. And so in this case, what I did was I subtracted positive 9, but I ended up with negative 9. And so the thing that I subtracted and the thing that I ended up with are not the same as each other. So again, nope, that does not work. There's no identity property for subtraction. So all three of these properties held for addition. None of them hold when it comes to subtraction. And let me know if you have any questions on any of that. Another thing we looked at with addition was closure, and I'm going to have you try a closure question. True or false? The set of whole numbers is closed under subtraction. And the language there means if we do subtraction on two whole numbers, is this a closed system? Oh, and this is, I'll make a poll for this one. Quick one. So, true or false, the set of whole numbers is closed under subtraction. What's that saying is, if you subtract two whole numbers, do you get a whole number back every single time? A lot of times we think a true-false question might be pretty easy, but sometimes they're not. Sometimes they're a little more challenging than that. And remember, to say something's true, it has to be true all the time, no exceptions. To say something's false, we just need to find that one exception that might be out there, and if we find it, then we say false. Let's go 20 more seconds, and then we'll talk about this one. All right, let's see how we did here. Okay, fairly strong agreement. A couple of I think it's true. So let's take a look here. The first thing we have to remember when answering a question like this is, what is closure anyway? And closure means if I use two numbers from this set, do I end up with a number that's also in that set? We have to remember what whole numbers are. Whole numbers are, let's see, that's the natural numbers, but also a 0 in there. So it's 0, 1, 2, 3, 4, and that keeps going forever. So these are the numbers I have to pick from. And I'm going to subtract, and we're going to see if this works. Now, I might do like 14 minus 2 and get 12 and say, well, that's a whole number, that's a whole number, that's a whole number. Kind of looks like it works. But remember, one example that works doesn't make this true. It has to be true all the time, every single time, no exceptions. If I want to show it false, I just need to look for something that doesn't work. And the way that I'm going to get something that doesn't work here, it could take a little trial and error. But if I do a smaller number minus a bigger number, I'm going to get a negative answer. Now I have whole number minus whole number, and this is not a whole number. And so right here is a perfect counterexample to say, well, set of whole numbers is closed under subtraction? No, it's not. And right here is my proof that this has to be false. because I can do whole number minus whole number and get an answer that's not a whole number. Any questions on what we did there? All right, outstanding. Remember, when you're trying to answer one of these true-false questions, you're trying to find something that would make it false. That's how you go into it. And if you try really hard to find something to make it false and you can't, then you've kind of convinced yourself that it's true. But if you can find something that proves it's false, then you can say false and you're all done. Okay. Just like we have a standard algorithm for addition, we also have a standard algorithm for subtraction. And so if we want to do 732 minus 155, we can subtract here. Kind of like our approach to addition, while it might be our normal thing would be to subtract bigger numbers first. If I was subtracting money, I'd subtract the hundreds, then the 20s, then the 10s. But our algorithm that we're going to use, our standard algorithm, is going to have us start in the ones place. And I look in the ones place, and I would like to do 2 minus 5. Well, I can't do that. I don't have enough to do 2 minus 5. So what we're going to have to do then is we're going to have to borrow. And what I'm going to do over here is I'm going to borrow 10 from the tens column. And I'm going to put those in the ones column. So I'm going to reduce this by reduce that by 1. That's 10 that I've knocked down there because that's the tens place. And I'm going to increase this by 10 because I've borrowed 10 from the column next to it. My guess is this is very comfortable for you as far as the process goes. The language might be a little different or new or something like that. So let me know if you have questions about it. But essentially, I'm borrowing 10 and putting them in the ones column. I took a 10 from here and put that 10 right here as ones. Now I can subtract. I can do 12 minus 5 and get 7. Okay, great. Now I'll move over to the tens column here. And I look in the tens column, and I would like to do 2 minus 5, but I can't. Can't do 2 minus 5. So I'm going to have to borrow again. So I'm going to look over here to this hundreds column, and I'm going to borrow 100 from the 100s column. Knock that down by 1 because I've reduced it by 100. That gives me 100 to put back into my problem, and I'm going to put that 100 in the tens column. And when I put that in the tens column, that means I'm going to add 10 tens, and instead of a 2 there, I'm going to have a 12. Now I can subtract 12 minus 5 is 7. Finally, I can go over to the hundreds place. 6 minus 1 I can actually do, and I end up with 577 as an answer. That's our standard algorithm where we start in the ones place and then borrow from the column that's next to it if we need to. Let me know if you have any questions about that. All right, let's look at some alternative algorithms for subtraction. I've seen this called the Indian algorithm for the country of India. I've also seen this called the European algorithm. I've had students from Eastern Europe, especially Poland, Hungary, Czech Republic, those places, that this is how they learned how to subtract when they were young. So I've seen this called both things, both the Indian algorithm and the European algorithm. So either one of those names goes with this. It's a little bit different than what our standard algorithm is, and we're going to do the same problem. We're going to do 732 minus 155. And the way this one works is instead of starting in the ones place, instead of starting on the right, we're going to start on the left. We're going to do this left to right. Some folks think this makes way more sense because that's how we read, is left to right. If I was going to count numbers, I'd start with the big ones, not the small ones. So there's some value in that. Let's take a look at how this one works when we go from left to right. So I'm going to start out in the hundreds column and do 7 minus 1. I can do that. That's 6. Okay, no problem there. I'm going left to right. I move over to the tens place, And I would love to subtract here 3 minus 5, but I can't. So I am going to have to borrow. What's different about this algorithm, the way that this algorithm works, is I'm going to borrow from the number that's in the answer. So I'm not going to borrow from these numbers up here. Instead, I'm going to borrow from the numbers that are in the answer. So I'm going to reduce this by 1 because I'm borrowing 100, and I'm going to take that 100 and put it over here as 10 tens. And now I can subtract 13 minus 5. That would be 8. Done with the tens column. Now I'll move to the right and go to the ones column. And I'd love to do 2 minus 5, but I can't. I can't do 2 minus 5. So I'm going to have to borrow again. I'll go to the column next to it, which in this case is the tens column. And I'm going to borrow from the answer. So I'm going to reduce that by 1. I'm taking 10 from the tens column and putting that 10 in the ones column. And now I can subtract over there. 12 minus 5 gives me 7, and my answer is 577. Just to sort of verify this a little bit, that is the same answer I got the other way, 577. And here we're borrowing from the answer when we go left to right. That's the difference with that algorithm. It works, it's great. If you love it, you can subtract that way. If you're not that comfortable with it and you don't like it, you don't have to. One advantage I do see to this, and I've had students tell me this that were raised on this method. One thing that they like about this method is you never have to cross the same number out twice. That is something that happens with our standard algorithm. You look right here. We started with a 3, we crossed it out, made it a 2, and then we crossed that out and made it a 12. That is challenging for young students because the mistake that sometimes gets made is this ends up being a 13 up here because they forgot to reduce it to a 2, or they weren't sure what to put the 10 on. And it's because we have to change that number 2 times, it adds a layer of difficulty. I'm not saying this method is inferior. I'm just saying that that is an aspect of it that sometimes is challenging, that students who learned this method when they were kids say you never have to cross out the same number twice because you're crossing out down here in the bottom. So that's one thing that you might find favorable about the Indian or European algorithm. Let me give you one to practice. We're not going to do a poll because I know you'll get the right answer. I just want to give you a chance to try this using the Indian algorithm and see how it goes. And then I'll do it in a minute or two, and then you can compare what you have with what I have to make sure you understand how this process actually works. It can be easy to think there's only one way to subtract, and then we kind of realize, well, maybe there is more than one way. There's more than one way to add. We saw partial sums and lattice on Monday. Maybe there's more than one way to subtract, and we're looking at the Indian algorithm right now. So what we're going to do here is 40 minus 27, and we're going to use the Indian algorithm, also known as the European algorithm, to solve this. What I hope you did was, and the clues up there at the top of the page are really helpful. We're going to go from left to right. So I'm going to start with 4 minus 2. Okay, that's no problem. I get 2. When I move over to the ones place, I want to do 0 minus 7. I can't do that. So I'm going to need to borrow. But I'm already done with this place. So I'm not going to borrow from that 4 at the top. Instead, I'm going to borrow from the answer, which is the 2 at the bottom. I'm going to take 10 from there, which allows me to increase this by 10. And then 10 minus 7 gives me 3. And sure enough, 40 minus 27 is 13. We know it's going to be 13. That's how it works with the Indian algorithm. And here we just had one place value position. I want to give you a chance to ask questions on this, and then I'm going to let you try one that actually goes over to the hundreds place instead of just ones and tens. All right, here goes. 312 minus 175. Try that one using the Indian/European algorithm. I'll give you a minute or two to do it, and then we'll talk about it together. This one has an extra step from the last one, but the philosophy is the same. We go left to right, and we borrow from the answer. All right, let's see what this looks like as I go through it. If you see something that you're unsure of, you had something different, you don't know why that number is there, you just say something, and we'll make sure you get squared away. All right, so for this algorithm, we go left to right. So 3 minus 1 is going to be 2, no problem there. And then I move over to the tens place, and I would like to do 1 minus 7, but I can't. I'm going to have to borrow. So I'm going to borrow 100 from the hundreds place, and I'm going to write that down as 10 tens in the tens place. So that number becomes 11. And then we'll do 11 minus 7 is 4. Okay, doing good. Now we'll move over to the ones place, and I'd like to do 2 minus 5, but I can't. So I'm going to have to borrow. And so I have to borrow 10 from the answer, and then this goes up by 10 and becomes 12. And then 12 minus 5 is 7, and so our answer there is 137. We go left to right, and we borrow from the answer. Let me know if you have any questions about that particular method. Outstanding. And Laura, you can tell us whether you like them or not, or you don't have to. I just was throwing that out there because you like to let us know. I figured I wanted to make sure that door was open for you. And for anybody else, for that matter, comments are perfectly acceptable and encouraged. Okay, okay, no good on the Indian algorithm. Let's see if you like the New Zealand algorithm. So for the New Zealand algorithm, we don't do any borrowing at all. There's no borrowing involved. Let's take a look at this. If we want to do 732 minus 155, if I want to subtract those. Now, it says no borrowing. Well, how in the heck are you going to do this without borrowing? Which is an excellent question to have. The way the New Zealand algorithm works is this one, we go right to left. So we're going to start in the ones place, just like we would in our standard algorithm. We're going to go right to left. And I'd like to do 2 minus 5, but I can't do 2 minus 5. But I'm not going to borrow. What I'm going to do is I need this number right here where the 2 is to be bigger. So I'm going to increase that number by 10. I've increased the top number by 10. In order to keep this problem balanced, in order to keep it equal, if I increase the top number by 10, then I also have to increase the bottom number by 10. Don't write this down. I guess I could make that a 15, but that's not going to do me any good. That doesn't help me at all. That puts me right back where I started, where I can't subtract. So if I want to make the bottom number bigger by 10 in a way that works, I'm going to increase this from 5 to 6. So what I've done here is I've made the top number bigger by 10. I've made the bottom number bigger by 10. And now I can subtract. In the ones column, I'll do 12 minus 5 and get 7. I'm going to move over and use the exact same philosophy in the next place value, in the tens column. I would love to subtract here 3 minus 6, but I can't do 3 minus 6. So what I'm going to have to do is I'm going to have to make this number on top bigger. I'm going to make the top number bigger. I'm going to bump this up to 13. What I've done is I've added 10 tens. I've added 100 to the top. Well, if I add 100 to the top number, then I also have to add 100 to the bottom number, and I do that right here. Now I can subtract. That 13 minus 6 will give me 7. 7 minus 2 will give me 5. And sure enough, I get 577, which is the same answer we got for this problem when we did it before. Here, we don't do any borrowing at all. Essentially, what we're saying, and I can speak in the language of other number bases since we did so well with those, is that 7 hundreds, 3 tens, and 2 ones, if I wanted to subtract 100, 5 tens, and 5 ones, well, that problem, 7 hundreds, 3 tens, 2 ones, minus 100, 5 tens, 5 ones, is the exact same problem as 7 hundreds, 13 tens, and 12 ones, minus 2 hundreds, 6 tens, and 5 ones. I have the difference is the same, and that's why it's okay to do this. I find this to be extremely clever. There's no borrowing at all. There's no moving anything between place values. We're strictly just, I'm going to make this bigger by 10, make this bigger by 10. I'm going to make this bigger by 100, I'm going to make this bigger by 100, and now subtract what I have. I'm going to have you try one and see if you can do it using the New Zealand algorithm. Here goes. I'll just give you a couple minutes to practice it, and then we'll do it together. And that's 312 minus 175. Here again, you might like the New Zealand algorithm, you might not. That's okay. I want you to be aware of the fact that there's more than one way to subtract, and these algorithms work every single time. They're repeatable, they work every time, they give correct answers, so they're totally valid. I think classroom use on these might be, it might go two directions. Number one could be if a kid struggles with the standard algorithm, maybe you let them try something like this. It also could be that you have a kid that subtracts like this because that's what their parents taught them. And it's good to go, oh yeah, I see what's going on here. I get this. I appreciate what you're doing there. And you can keep doing it that way. Or if you would like to try our standard algorithm, then that's okay too. We can move you in that direction. So I think this has both directions to it. All right, let's take a look at this one. We're going to go right to left. We're going to increase both the top and bottom numbers. We're not going to borrow anything. So I'd like to do 2 minus 5, but I can't. So I need to make this bigger by 10. And to go along with that, I need to make the bottom number bigger by 10. So I'm going to bump this up from 7 to 8. Okay, I can do 12 minus 5 now. In the tens column, I would like to do 1 minus 8, but I can't. 1 minus 8 I can't do, so I need to make this bigger. And in making that bigger, I'm adding 10 tens because I'm turning that into 11 tens. It was 1 10 before, now it's 11 tens. I've added 10 tens, which means I've added 100 to the top number, so I need add 100 to the bottom number. I can subtract 11 minus 8 and get 3. I can subtract 3 minus 2 and get 1, and 137. That's the same answer we got for this one when we did it with the Indian algorithm. Let me know if you have any questions on the standard algorithm, the Indian/European algorithm, or the New Zealand algorithm. Different ways to subtract in addition to our standard algorithm. All right, fantastic. Our book will reference something called the counting up strategy. It's sort of the way you would instinctively solve a question like this. I'm just going to let you solve it, and then we'll kind of talk through it and see how it went. Marissa woke up at 5:52 a.m., went for a run, had breakfast, read the news, took a shower, and left for work at 7:35 a.m. How long was she awake before leaving for work? I'll make a poll for this, and I'll let you try it. And the way that the answers are phrased there, that's hours and minutes. So like the first choice, 1:17, that's 1 hour and 17 minutes, just to make sure you understand what those responses mean. Go another 20 seconds on this one, and then we'll talk about it. Oh, if you don't come up with any of those, pick the one that's closest to yours. That way I'll know you've had enough time. And then because you know you didn't have one of those answers, you can talk about it with us if you need to when we go through it. All right, let's see how this one went. Okay, strong agreement here. That's excellent. Very good. Okay, let's talk about it. There are a couple of different ways you can go about solving this. And one of those ways, and this may or may not be the method that occurred to you here, is to say, well, it's 5:52. To get to 6 o'clock, that's 8 minutes. And then from there, to get from 6 o'clock to 7:35, well, that's an hour and a half, or excuse me, an hour and 35 minutes. So if I go another 1 hour and 35 minutes, and I put that together, it's an hour and 43. Another way to go here, maybe a little more explicit, I probably should have done this one first, is say, all right, and then I'm going to go from 6 to 7, and that's 60 minutes. And then I need to get from 7 to 7:35, and that's 35 minutes. And then when I put all this together, I've got 1 hour, and then 35 and 8, that's 43 minutes. And we end up with an hour and 43 minutes. The reason this is called the counting up strategy is that's kind of what we were doing there. Oh, good, Lee, I'm glad. Is we're just counting it. I'm counting up to 6, counting up to 7, counting up to 7:30. Like I said, some of you may have done something along these lines and said, well, I'm going to do the 8 minutes to get me to 6 o'clock, and then another 1:35 to get me to 7:35, and I put those together and end up with 1:43. Another way you could go here, and some of you may have done this, is say, well, it's 5:52 right now. If I just go forward 2 hours, that's 7:52. That puts me at 2 hours. Although 7:52, I went too far. Now I've got to back up a little bit. And from 2 hours, I need to subtract to get me from 7:52 back to 7:35. Well, I need to go backwards 17 minutes. So I'll take 17 minutes off of my 2-hour mark and end up with an hour and 43 minutes. Any of these approaches, counting up from 5:52 to 6, then to 7, then to 7:35, counting up from 5:52 to 6, and then all the way to 7:35, or counting it in such a way that you just go ahead and go past it just to get a whole number of hours, and then subtract what you need to land in the right place. Any of those approaches are fine. You may have done something different from those three, and if you did, you can share that with us if you want to. Most important thing is there's more than one way to answer a question like this. Just be careful as you do it. Most people will do this counting up approach over here, and that's why you'll see the counting up strategy referenced in the book. Are there any questions about what we did there? All right, excellent. A little bit of problem solving. Penelope was driving from Boulder City, Nevada to Bullhead City, Arizona. When she left Boulder City, the odometer in her car that says how many miles she's driven read 72,105. She made it to Bullhead City and headed back toward Boulder City. And when she was 58 miles from Boulder City, her odometer read 72,217. And then the question says, how far is it from Boulder City to Bullhead City? Now, there's a whole lot going on here in this question. So nobody expects you to just say the answer. We're going to go through a little bit of a process, and we're going to do some problem solving to get our answer here. Anytime there's a chance to draw a picture, even if it's extremely basic, I think it can be helpful. So if we start over here at Boulder City, and we're driving over here to Bullhead City. And when she left Boulder City, her odometer in her car read 72,105. So in Boulder City, she was at 72,105. She hasn't gone anywhere yet. She hasn't even left, hasn't even started. But then what happens on her trip is that she drives all the way to Bullhead City and then turns around and comes back. And when she has 58 miles left to go, her odometer reads 72,217. So we've kind of taken all the information we were given there, and it was a lot of it. There's a lot going on with 2 different towns and going 2 directions and odometer readings and all this stuff. But now we've kind of boiled that down into this picture where you go from Boulder to Bullhead City, and then you come back, and you have 58 more miles to go. The way we're going to approach this is we're going to say, let's just have Penelope finish the trip. So she's here at 72,217, and she has 58 miles to go. Essentially what we're saying is, what will her odometer say when she finishes the trip? And to get that, we're just going to add these 2 numbers together. 72,217 plus 58. We're going to have her go ahead and finish the trip, and when she does, her new odometer reading at that point will be 72,275. Please let me know if you have any questions on that. Essentially, we said, what's her odometer going to be after she drives those 58 miles that she has left to get back to Boulder City? If we're good on those 2 green numbers, I think we're kind of home free here. Outstanding. Okay. So now the first thing we want to find out about these green numbers is, well, okay, how far did she drive total? So we're going to subtract 72,275 minus 72,105. And that's 170 miles. Careful, that's not the answer to our question. We want to go back and reread that question again. If the question said, how many total miles did she drive? Then 170 would be our answer. But our question here was, how far is it from Boulder City to Bullhead City? How far is it from here to here, not the coming back part. What do I have to do with this 170 to finish this off and get my answer? Perfect, Laura. Yeah, and Stephen, you're probably right there with her, which is great. Yeah, if it's 170 miles round trip, then I need to divide that by 2 to find out how many miles it is one way, and that's 85. So how far is it from Boulder City to Bullhead City? 85 miles. There was a lot going on in this question when we first read it. Drawing a picture definitely helps. Drawing a picture gives us a, okay, we're going to go this way, and then we're going to come back that way. But we're not going to make it all the way. We're still going to have some to go. That's all right. I'm going to pretend that I'm going to go ahead and finish this drive. Now I know how far Penelope drove in total. And then if I want to know the distance one direction, I'll just cut that in half. Let me know if you have any questions on any of that before I have you try one like it. Okay. Joshua was driving from Billings, Montana to Lewistown, Montana. When he left Billings, his odometer read 42,177. He made it to Lewistown and headed back toward Billings. When he was 38 miles from Billings, his odometer read 42,389. How far is it from Billings to Lewistown? I'll set up a poll for this and I'll let you try it. And all of our numbers in the problem are in miles, so all those answers are in miles. If you get an answer that you don't see there, pick the one closest to yours so that I know you've had enough time. And then make sure you ask about it if our explanation doesn't clear it up. This is the type of question you see in homework, maybe on a quiz, maybe on an exam. So give it a shot. It reads more complicated than it turns out to be in the solving process, but I want to give everybody a chance to solve it. We'll go another 30 seconds, and then we'll talk about this one together. Okay, let's see how we did. Okay, some agreement, but spread around a little bit. A lot of 212s. All right, let's take a look at this one, and you can ask whatever you need to, if you need to. So here again, if I have the opportunity to draw a picture, I'm going to do that. And so the picture I'm going to start here is not going to be very elaborate. I'm just going to make sure I have Billings and make sure I have Lewistown. And Joshua is going to drive from Billings to Lewistown. And when he drives from Billings to Lewistown, his odometer says 42,177. So when he started out, that's what his odometer said. He made it to Lewistown, and then he's going to turn around and head back to Billings. But he's not going to make it all the way there when he looks at the odometer. He looks at the odometer, and he's not quite back yet, and it says 42,389. He hasn't made it all the way back to Billings yet. He still has 38 miles to go. So he has 38 more miles left to get to Billings. So what his odometer reading is going to say when he makes it back to Billings is going to be these two numbers added together. We're going to add those two together because we're going to take the 42,389 that's currently on his odometer. We're going to add 38 miles to that. When he makes it back to Billings, his odometer is going to say 42,427. So he started out with 42,177. He ended up with 42,427. So the total distance driven round trip would be 42,427 minus 42,177. That's 250 miles. Nobody had that as an answer, which is great because it's easy to forget that divide by 2 step. But what that gives us is the round trip distance, Billings to Lewistown and back. What we want is just how far is it from Billings to Lewistown, just one direction. So we'll cut that in half and find out that it's 125 miles from Billings to Lewistown. Let me know if you have any questions, if that explanation didn't clear that one up for you. All right, very good. I really just have one more thing to say. In your homework, number 31 is a question that you could use trial and error for it. You could use algebra for it. If you use algebra for it, be careful when you set up your equations. And I also want to point out that that's not really the type of question that that you can expect to see on an exam, probably not even on a quiz. I just think it's a fun, challenging question that I want you to try, and you can try to solve it using either trial and error or algebra.